In this video, we're going to be focusing on enthalpy, and we're going to be looking at some thermochemical equations, and we're going to be utilizing something called Hess's law. Enthalpy is what's called an extensive property, and what that means is that the amount of energy that is released or consumed during a reaction is based on the amount of the substance. So, for example, I have some magnesium clumps here, and hopefully this makes sense, but the more magnesium you burn, the more energy will be released. So if we have a small amount of magnesium, a small amount of energy will be released. However, the more magnesium you have, the more energy will be released. So that means that enthalpy is an extensive property. It is dependent on the amount of the substance. There are two things that we need to remember when we're looking at thermochemical equations. The first thing is that if we multiply the reaction by a certain amount, we want to make sure that we multiply the enthalpy by the same amount. So I'm going to go ahead and give you an example. We've actually looked at this equation before already. We have some solid carbon, it reacts with some oxygen, and it produces carbon dioxide. And our delta H is a negative 393.5 kilojoules. Remember that negative means that energy is being released, so this is an exothermic reaction. Now, if I were to multiply the reaction by 2, and if I were to double the amount of everything in there, I would also need to multiply the enthalpy by 2. So I might end up with an equation that looks like this. I now have 2 moles of carbon plus 2 moles of oxygen, and it produces 2 moles of carbon dioxide. And now, instead of 393.5 kilojoules of energy being released, I'm going to be releasing 787 kilojoules. So whatever you multiply the reaction by, you need to make sure that you multiply the enthalpy by. The second property of thermochemical equations is this idea of flipping the reaction. And the rule is that when you flip the reaction, you need to change the sign of the enthalpy. So here we have the same equation. So again, we have carbon and oxygen, and it reacts to form carbon dioxide. This is an exothermic reaction. But if we were to think about this reaction and we were to flip it, hopefully you would see that instead of an exothermic reaction, it would become an endothermic reaction. So here I went ahead and I flipped the reaction. Notice that my carbon dioxide has now become the reactant. So in order for carbon dioxide to break apart into carbon and oxygen, energy is needed. And how much energy? Well, the same amount of energy that's released in the first equation is the amount of energy that's going to be consumed in the second. So we are flipping the entire equation, and we change the sign of our delta H. These two rules and these two properties of thermochemical equations are going to be really helpful when we look at Hess's law. The enthalpy change of a reaction is equal to the sum of the enthalpy of the individual steps. Now, what does that mean? It means that some reactions happen in one step, but most happen in a series of steps. So when we look at a thermochemical equation, it's kind of a simplified. We are looking at what reacts and what is produced. But in reality, when we think about a reaction, usually they happen in several steps. It's not just a product to reactants. There's what are called intermediates. And if we were to think about that, the amount of energy released is equal to the sum of those individual steps. And that's going to be key when we look at Hess's law. So when we're dealing with Hess's law problem, there's a couple things that we need to do. The first thing is we need to identify what our goal reaction is, and that's going to be kind of like our main reaction. Once we identify that goal reaction, we're going to be paying attention to that goal reaction, and we're going to identify what the products are and what the reactants are, and we also need to identify how many moles we have of each. Once we've done that, we're going to be looking at our different step reactions. And what we're going to do is that we're either going to flip a reaction or we're going to multiply the reaction in order to get the same product and reactants of the goal reaction. Once we have that, the products in one reaction will cancel out the reactants in another and vice versa, and then we could add up our energies. Now this might not make sense right now, so we're going to go ahead and we're going to look at an example problem that hopefully will become more clear. So here's my goal reaction. I want to turn graphite into diamond. So C of graphite is C of diamond. And I'm given two reactions. So I'm given these two reactions. So I have graphite plus oxygen will produce carbon dioxide, and I have diamond plus oxygen will produce carbon dioxide. So we're going to be looking at this. Now, the first thing that you want to ask yourself is, what are my reactants and my products in my goal reaction? Well, if we look at the goal reaction, what we see is we have 1 mole of carbon graphite and we have 1 mole of diamond. And we want to be able to turn that, and we want those to represent what we see in the equation. So if we look at equation number 1, we see that it actually has 1 mole of graphite in it, and it has it as the reactant. So what we're going to do is we're going to keep that reaction. So because it has the C of graphite with the right amount and in the right place, meaning in the right place, I mean like as a reactant or a product, we're going to keep that reaction. We're not going to do anything to it. Now in the second one, what we see is that equation number 2 has the C of diamond, but it has it as a reactant, and we want that to be a product. So what we need to do is we need to flip the reaction. We need to create that C of diamond, and we need to move it from a reactant to a product. So we're going to flip that entire reaction. So what we end up having is we end up having these two reactions. So notice that I said that we kept the first one, and in the second one, notice that we flipped it. And when we flipped it, we also changed the sign of our delta H, and that's really important. Now, what we want to do is we need to start canceling things out. We need to start canceling out what is in the product of the first reactant and what's in the reactant of the second. So what we see is that carbon dioxide is a product in the first and a reactant in the second, and those will actually cancel out. The 1 mole of oxygen as a reactant in the first and a product in the second will also cancel out. What is left over when we cancel those things out is our goal reaction. So here I went ahead and I canceled out my carbon dioxide, canceling out my oxygen, and what's left over is graphite turning into diamond. So now that we have our goal reaction left over, if I were to kind of like add those two reactions, I can go ahead and I could add my delta H values or my change in enthalpy values. And when I do that, I get that my goal reaction, the delta H or the enthalpy of my goal reaction is a positive 1.9 kilojoules. Now, this problem that I just did is done a little bit differently in your textbook. You could choose to do it either way. This is the way that I've learned to do it, and I've always done it. Now, I'm going to go ahead and I'm going to be creating another video where I do another HESS'S Law problem that might be a little bit more complicated. So if you need another example, make sure to check out the next video, which will be called HESS'S Law number 2.